Hi, thanks very much for inviting me to speak here. So this is joint work with those people here, Joseph, Mario, Yiming, Spencer, Suga, Sina, and Steve. And the list is not closed. So at the end of the talk, there will be a call for contributions if you are interested in joining the project. Um, okay, so the talk will be structured in roughly three parts. The first part will be a hopefully accessible and like generally understandable introduction to what I mean by certifying synthetic mathematics. And I know that Steve has already presented this to some extent last week in this seminar, but I have maybe a slightly different perspective on things. And anyway, I wanted to give a motivation for this project. Then the second part will be a more technical sort of in the weeds description of what we have actually done. And the third part will be some list of like open problems or maybe just things that we would like to see happen and things that would be good places to contribute. Okay, so synthetic mathematics. So this terminology, synthetic, in mathematics at least, has come from geometry. And the idea there is that there are two approaches to geometry. There's the synthetic approach of Euclid, and there's the analytic approach of Descartes. Oh, actually, maybe before I go on, just one more thing. Interruptions welcome. So if anything is unclear, please ask questions. It's better to do that than for me to go on and leave everyone confused. All right, so this is proposition one in book one of Euclid's Elements. And the statement is that if you have a finite line segment PQ, then you can construct an equilateral triangle that has PQ as one of the sides. So I'm now going to give you two different proofs of this proposition. So on the left-hand side, let's begin with doing Euclid's proof, the way that it was done in the Elements in the original text. The way that works is, well, we have this line PQ to begin with. That's our given data. And then how are we going to construct the triangle? Well, first we use the compass, which is this tool that is one of the allowed tools that you can use in the constructions in the elements, to draw a circle whose center is at P and which goes through Q. And then we use the compass again to draw another circle that is centered at Q and which goes through P. And then we observe that by the laws of geometric reasoning, these two circles have to intersect. So there's some point R at their intersection that we can choose to be the third vertex of our triangle. And then using some reasoning about how, any line from the center of a circle to the edge has to be equal in length to any other such line, we can show that this triangle is equilateral. Great. So that's Euclid's proof. Okay, here's another proof. I'm not saying that that is what Descartes did. I don't actually know what Descartes did, but it's like Descartes' style, let's say. So in Descartes' geometry, points are understood as pairs of numbers. So this, at the time, I mean, maybe it's obvious to us now, but at the time that this was done by Descartes, this was like a new thing, an innovation, a great new idea, that you can actually understand these things in terms of coordinates that are pairs of real numbers. So let's assign P and Q some coordinates. So we have X and Y for P and X and Y for Q. And then the way that you can construct R, the third vertex of this triangle, is you don't do any drawings with those tools. You just do like vector algebra, right? So you take the vector from P to Q, and then you rotate it by 60 degrees because all the angles in an equilateral triangle in the plane are 60 degrees. And that gives us the third vertex R here. And then we can compute some norms and show that all these three segments are same length, so the triangle is equilateral. And the way that you would do this is, you do calculations in like some ring, I mean, specifically the real numbers. So the thing I want to point out is that these proofs are, in some sense, really quite different because in this proof, we never assigned any like numbers to those points, and we never said that, oh, this line segment has line length 3 or something, and so forth. And this is supposed to be the difference between synthetic and analytic geometry. In the analytic approach, we take those primitives that in Euclid's picture were irreducible and did not have any further internal structure, like pairs of numbers, and we break them apart in terms of these finer things like coordinates. So, okay, that's great, but can we make this difference more precise and more formal? And the answer is Yes, so we can do it using modern model theory. I mean, because really the difference between those two things is that Euclidean geometry is some kind of, let's say, first order theory, and the Cartesian plane, I mean, real numbers squared, is a model of that theory. So let's say that phi is this sentence in the first order language of geometry. So it says that for any 2 points P and Q that are not equal, so this is like the data of a finite line segment. There is some other point R with properties that I won't spell out, but basically they're supposed to say that it is the third vertex of this triangle. And by the way, geometry is italicized here because I don't want to commit to like specifically what kind of geometry I mean. It's just let's leave that vague. Well, so if we view this situation from this perspective, then the left proof and the right proof, I mean, the picture and the kind of vector algebra, they're actually proving different things. And they're not just different proofs, they are proving different statements. The left proof is proving that the first order theory of geometry, like formally proves this sentence, phi, oh, sorry, this phi should have been that phi. They're supposed to be the same. And then the right proof is showing that the model of geometry given by the Cartesian plane validates this sentence, right? So this is like a semantics sort of thing. It's truth about some model, and this is a syntactic provability sort of thing. It's provability in some theory. And the relation between them is, of course, soundness. So the model is a model, which means that, and we write it like that to say that the R2 plane validates all the axioms of geometry. Again, I'm leaving geometry a bit vague here. And by soundness, this probability statement implies the truth statement. But they're not exactly the same because this one is actually more general. So famously, if you take geometry without the parallel postulate, then it suddenly applies to all these other kinds of objects that are not the Cartesian plane, but maybe are like hyperbolic space, like this picture of a saddle here, right? So this same statement will be true about hyperbolic space. But it is true, like the way you could prove it is you do the Euclid style proof in first order logic, and then you apply soundness and you get to know that this is true of the saddle. You cannot just, on the other hand, take the proof that we did in Descartes style about vectors and so forth, and directly transport it to here, at least because we used 60 degree angles over there, and that's not what happens in a hyperbolic space. The angles don't add up to 180 degrees. So in some sense, the left-hand side is more general. Okay, and that's the synthetic approach. Great. So that's all I want to say about that. Is everything clear? I'm assuming if
Yep.
no one raises
Yep.
a hand, then there are no questions. Great. So now let's ask a slightly different question, although it will end up being related, of course. When we prove things in Lean, what are we really proving? Okay, so let's say we write down this theorem. I call it 1, and it's a great theorem of number theory that 2 + 2 = 4. Okay, and we can do it by raffle. Well, you might ask me, what do you mean? What is that question supposed to be? Of course, I just proved that 2 + 2 = 4. There's nothing more to it. Aha, but here I come, the logician, and tell you that actually what you have proved is, in fact, that the formal system called Lean, which is some kind of dependent type theory with proof irrelevant propositions and universes and stuff. Well, that type theory says that according to all of its rules of inference, the term RFL is a term of type 2 + 2 = 4. Okay, and the difference in perspective is that in the left-hand side we view our Lean proof as, or like Lean itself as being our math, our ambient universe of mathematics. And the right-hand side we step outside the system and view it kind of from the outside. Like externally and say, okay, here is this formal system. It's called Lean, and it proves this thing. I'm also introducing some notation here. This is very well known to type theorists and logicians, but just to explain, we have this ternary relation. On the left-hand side here, we have the variable context. It's empty for now. That's what the dot means. I will explain. I will give an example next where it's not empty. And here we have the term, and here we have some type. Of course, if you've ever written Lean, this is what the goal state or the tactic state looks like, right? So it's the same thing. There's also a minus on the lean here conspicuously. I will explain that in a second. Okay, next example, we prove a theorem of number theory 2, and this one is parameterized by a natural number. This is just to illustrate that in general, the context stores the variables that our theorem refers to. So here we have a number n. Okay, next theorem, step up in complexity, Fermat's theorem. We don't have that yet. Maybe if Kevin's project succeeds, then at some point it will exist in Lean. Presumably, the proof of that thing will be very big. So it's not just going to be a simple term like REFL. It will be tons and tons of lemmas in the library. And the reason I'm mentioning this is I want to illustrate a bit of a difference between these two proofs at the beginning and the kind of hypothetical proof of Fermat's theorem. Well, these two proofs are actually in some theory that we could call lean minus. This is a bit of a callback to a talk about lean for less that happened here a couple of weeks ago. I don't mean the exact same system called lean minus as in that talk, but I mean something similar, which is to say it's lean, but importantly, you don't use the axiom of choice and you don't use the law of excluded middle, and there are just fewer features of the type theory in general that you're using in this proof, okay? Whereas presumably whatever proof there might be of Fermat, that will use all the bells and whistles that Lean provides. So I write that theory as just Lean versus a simpler one, a Lean minus. Okay, and the general form of this statement is that we could have some kind of theorem called for, which makes a bunch of assumptions, gamma 1 through gamma n. It has some type A, and it has some term t. And the way you would write that is that t is a term of type A, in this context, gamma, according to the theory T, and here T refers to the axioms that for depends on. Okay, so in Lean, you can print out the axioms that the theorem uses, and that is what I mean by the theory, plus the built-in rules. Okay, so like versus whether it uses the universe of propositions and things like this. Okay. I'll pause for a second in case there's anything. Okay, let's move on. So why am I doing all this? Well, the point is that if we take the external perspective, then it becomes part of mathematics, and you can start formalizing this stuff, and you can start proving things about it. And the reason that this is interesting and useful, although maybe it's a bit strange and logic flavored, is that, well, like in the case of geometry, the set-based model of type theory is not the only model. So if you can reflect these kinds of statements about how type theory proves something in Lean, let's say, or in a different proof assistant, then you can start using this fact that other models exist to maybe prove things about those models. And this is basically the goal of this project. Suppose we write down this inductive type in Lean. It's called the Booleans. It has two elements. And then the corresponding like judgment of type theory would be that the type bool is a type according to, again, Lean minus, because maybe we don't use all the features of Lean in this case. Now, the set-based model of Lean, which was spelled out, for instance, in Mario Canero's master's thesis, can give you an interpretation of that type. So every type becomes a set in this case. And it's kind of what you would expect. It's a set with two elements called true and false. But importantly, this was a discovery of, I guess, the 90s. There are some interesting models of type theory that are not set-based. So one interesting one is based on groupoids. So a groupoid is a category where all the morphisms are isomorphisms, but also you can more or less just view it as some kind of undirected graph for the purposes of this picture. So, well, this is a graph with just two disjoint vertices, or like two disconnected components. The thing, though, now is that since we can build some kind of model where we interpret types as things with more structure than just the structure of a set. So in this case, we have the structure of a whole groupoid or a graph. We can consider some other groupoids which exist like in math, like this one here, and think, okay, what could we do in type theory to describe this groupoid? So if you just take like the system that the features that Lean supports, you, as far as I know, cannot describe this one. So maybe I should say what it is. Well, it's a single point, and then you have a whole bunch of loops around it. Um, and this is basically the group of integers with addition. Um, but having seen that this exists in the model, maybe we can start backporting in some sense features of the model into our syntax and add these kinds of strange inductive types like S1, which is a type that's pretty well known to homotopy type theorists, that contains one constructor for the base and another constructor for these loops. And the interpretation of that thing is going to be this groupoid that we wanted it to be. And that is basically how you get to homotopy type theory and the groupoid model of it. Okay, a technical note for experts: this groupoids do not model full homotopy type theory. They model something we call HoTTLean, which is a slightly smaller system. All right. So our purpose with this work is to internalize this whole picture of theories, type theories, and their models in Lean, and potentially try to use it to prove things about those models. So here are the steps of that. First, we formalize syntax of type theory and provability in the syntax. Then we do what I would call the reflect definition. So what that means is that we can write a definition in Lean, and then there is some command that allows you to automatically obtain a proof of the corresponding typing judgment in Lean. So something kind of strange about formal logics in general, I guess, is that they can often describe their own provability relation, and so can Lean, or at least in this case, Lean can describe the provability in some maybe smaller but related type theory. So we have some commands that automatically produce proofs of this thing for you. And this is very useful because you don't really want to write like formal derivation trees by hand or whatever. You just want to work in the system, whatever that means. So from the internal perspective, but still you might want to get the external proof for purposes of, constructing theorems that way. Then the next thing we do is formalize semantics for type theory. So this various models. And we use, or at least are working towards using this proof assistant from part 2 to reason about those models using those theories. Yeah, I'll pause for a second. Okay. So here is an example of how you'd use SynthLean. The API is somewhat oversimplified in this slide, but hopefully it gives you the idea. So this is Lean code, right? We can write axiom X is a type, and we can write another axiom called P, which is some point of type X. That's as it, that's the standard thing. But then the new thing that we add in this project is this reflect attribute. And what that does is it will automatically construct for us a reflection. So for instance, the reflection of P is the structure of type reflected axiom. It keeps track of the axioms that P depends on. So P depends on X, right? Therefore, that's the list here. It stores the type of P as some deeply embedded syntax, which I will get into in a second, but here it is. So the type of P is X with a bunch of junk around it. And then it also importantly produces a proof that the type of P is well formed according to the rules of dependent type theory. So we have taken this external judgment of like Lean proves this and that, and have turned it into a proof in Lean so that we can use it for reasoning about models. Right. Then moving on, we could define this other point Q, which let's just say that's defined as P. And then on the side of the semantics, supposing we define some kind of model, this would be a category with lots of structure. I can't really get into that in this slide, but just suppose we have a model of type theory. And suppose we have given some semantics to x and p. So these are these.
Mhm.
Sorry.
No, sorry.
Okay. The mx is supposed to be the intended semantics of x, and mp is the intended semantics of p. They're both arrows in a category because that is how, categorical semantics and models work. Um, then we can construct an interpretation of the theory consisting of two axioms, x and p, those ones we wrote down here, in the model M, just by sending the axiom x to its semantics and the axiom p to its semantics. And then we can prove various things about the semantics. Like, for instance, if we interpret Q, this definition here, then it's equal propositionally to the semantics for P, which is what you would expect. But of course, besides doing the simple thing, we can do much more complicated things with the interpretation. Okay. So that's it for the introduction. I'll pause here again for a second in case people have questions, and then I'll move on with some more technical details.
So I have a question.
Mhm.
Yeah, hi, Andy Pitts here. So presumably you can't throw any valid bit of lean at reflect and get an answer. Is that
Right,
correct?
right.
So
So
what happens if you apply it to something and it barfs and it can't reflect that into your formalized theory? What do you see?
well, we have some error messages which maybe aren't as good as they could be, but hopefully explain to the user that, yeah, this is you're using a feature that is not supported, basically, is what the error would say. So,
And yeah, okay, thank you.
yeah. So like if you use proof irrelevant propositions, we don't support that in the embedding of type theory, and that would give you an error. Okay. Any other?
No,
All right.
I don't think so.
Okay, great. Then let's move on with the technical details. This stuff, I admit it might be a bit more opaque and, if you haven't seen it before, but maybe there are some experts in the audience who would be interested in this kind of thing. What are the components of this setup? Well, first we have a deep embedding of Martin-Löf type theories. With universes, pi types, sigma types, and identity types, as well as base constants. So these serve as the basic axioms of the theory, like x and p in my example. And so one thing you could write down here is not quite homotopy type theory because we have no inductive types at this stage, but maybe, well, you can certainly at least write down the univalence axiom. Then we have SynthLean, which is this embedded proof assistant that includes the reflect macro and some other features that I'm working on for working in those type theories in this kind of internal perspective. And the last thing we have is natural model semantics, so the categorical semantics for the syntax as well as the proof that they are sound for it. If you have seen categories with families before, natural models are similar to those. So the type theory that we define is more or less just very standard ordinary Martin-Löf type theory. One less usual thing is that it's stratified by the universe level. So all the judgments of the type theory are parameterized by the universe level that they live at. So what this means is that, for instance, A is a type at level L, or T is a term at level L, and so on. This is sometimes called universes à la Cocon. And the reason for that is the following rule of our system. So this rule says that you can only have a type universe at level L if L is less than some fixed finite number L max. And the reason for this is basically a Gödelian constraint. So we are going to build models of this type theory. If we had a countable or even larger hierarchy of universes, then you could not build a model of that of the kind that we want. There's a bit of a subtlety there that you can actually model a countable hierarchy of universes with using prop, the impredicative prop, but that would be kind of like a non-proof relevant model, and we want proof relevant models.
So another question, sorry. So am I right in thinking could you just remind me what the universe hierarchy and lean is like? I'm not a lean user, so I need to be reminded of it if you could.
Um, so at the bottom, it's the same
Do
one.
you have countably many universes, and do you have a sort of what I would call an Agda style closure of pi and sigma under it's they're not cumulative exactly, but
Right. They are not cumulative, and the rule for pi types is this one, which maybe
yeah,
answers the questions.
okay, yeah.
Um,
And you don't have a so I mean in Agda you could get around the problem you just mentioned in two different ways. One way is that Agda has a universe is omega plus one, etc. So you could have a countable collection and that would be fine. But
right.
also, of course, it does have inductive recursive definition. So actually, you could do the whole thing in one universe because
Mhm.
the universes there are pretty amazingly closed under constructions.
That's right. So lean does not include induction recursion or set omega. It has like universes, from one up to just natural number indexed universes. And it has a prop universe that's at the bottom of the hierarchy. But it is impredicative, so that gives it quite some proof logical strength. Does that answer?
Yes, it does. Thanks very much. Sorry for interrupting.
Oh, that's okay. Great. So the next rule we have is for pi types, and the reason I'm showing it here is that it is the same as leans, more or less. Um, So if we have a type at level L and the codomain is at level L prime, then the level of the pi type is the maximum of the two. This is chosen purely for like pragmatic reasons. So we want reflect to work, right? We want reflect to take some kind of term that the user typed in using potentially lean tactics. And we want all of that machinery to be translatable into our system without much effort. And one way to do it is just you define rules that are basically the same as leans. So that's what we did. Um, so that's why pi types are like this. And then one last rule to mention has to do with theories. A theory consists of a whole bunch of base constants with some types that they have. Like again, in the example, we had a base type x and a base point p in x. So if you have a base constant called c, and the theory says that it has some type a at level L, well then you can use it at that type and at that level. Okay. In Lean, the way this is formalized is kind of this old school approach from the 90s that we have some raw syntax of expressions, like here we have universes and pi types, let's say. And then over that raw syntax, we define mutually inductive propositions that say when a context is a well-formed context, so a context is a list of types. Also another judgment that says when a type is a well-formed type at level L, and so on. So that's the setup. Um, then on for the semantics, we have actually a couple of different kinds of semantics, but the one I will describe is natural models. So a natural model universe is such an arrow like here, the orange arrow, and it lives in some pre-sheaf category over a category of contexts. Um, so how do we interpret the syntax of type theory in such a setup? Well, suppose that we have a type A, which lives in context gamma, meaning that we can form the extended context gamma.a. And suppose we have a term T of type A, also in context gamma. Then we will model these things as follows. So we model the context gamma as an element of the context category CTX. So that's the interpretation, the skull brackets of gamma. We need a presheaf because this diagram lives in the presheaf category, and to do that, you use the Oneida embedding. Then the type is modeled as this arrow, or well, an arrow from the embedded context to the presheaf of types. And importantly, a condition that you need for this arrow to count as a universe is that pullbacks of all representable presheaves are representable. So if this guy is representable in the image of an index, then this guy also has to be in the image of an index. And we use this like the object of the category of contexts that is mapped through UNITA as the interpretation of the extended context. So that's how you interpret extended contexts using a universe. And finally, a term would be interpreted as a section of this map, meaning that if you go up and down, that's the identity. Right, so that's natural model semantics 101. In Lean, a universe is defined as this kind of structure. It's a pre-sheaf of terms over the category of contexts, another pre-sheaf of types, and then this map, which just to remind people what that map is supposed to do is it takes a term and projects out the type of that term. So the elements of term, in some sense, are really pairs of a term and a type. That's what this collection of things is. And then we have a map ext, which picks out the pullback, the corner of this pullback. So ext given a type down here will give us this gamma.a. That's the semantics. And then we want to interpret the syntax in the semantics. And this is well known to cause some trouble. We follow, again, the old school approach of like Thomas Streicher and Martin Hofmann from the 90s, where what you do is first you define some partial functions. So the interpretation function for contexts takes a syntactic context, so a list of expressions, and this might not be well formed, right? I mean, you can write any old kind of junk there. There's no reason that this is a sensible thing, but in case it is sensible, this map should give you an object of contexts, of the category of contexts. And similarly for types, there's some kind of interpretation function that takes a syntactic representation of a type, which again might not be sensible, but if it is well typed, then this function should be defined, as well as a context and gives us this arrow down here from the context to the pre-sheaf of types. The way you define it is by going by recursion on raw expressions. So for instance, for typing contexts, the recursion is like this. The empty context gets interpreted as the terminal object of the category of contexts. So we do assume that it has a terminal object. And then an extended context is interpreted in 3 steps. I mean, this is a program that does something. So the first step of the program is to try to interpret gamma. And this might give us an object X of CTX, or it might fail. But if it does work, then we move on to the next step where we interpret the type. Similarly, this might fail. If it does work, then we return the ext of that arrow. So to remind you, ext gives us this corner up here. And that is what should be the interpretation of the extended context.
Another question, I'm afraid.
Mhm.
Could you just parenthetically say in a little bit more detail how Lean deals with partiality with partial elements and so on? Is it that you just leverage the implicative prop and proceed as you would in a topos, as it were?
Right, that is correct. So this is implemented in Lean as a program of sorts. I mean, it's not really computable, but it is a program that lives in the partiality monad. And the partiality monad, what that stores is some element plus a predicate on. Sorry, so there is a domain type, an element of the domain type, plus a predicate on the domain that if is satisfied, then you're in the you're defined, otherwise you're not defined. And the predicate it does not need to be computable or anything. So you can write down what that amounts to in the end is that you can sort of have guard conditions or like checks of arbitrary predicates. So you can check arbitrary semantic conditions while you're doing this interpretation. Does that help?
Yeah, I can guess what you do. Another question is by recursion on raw expressions, could you just be a little bit more precise there? I mean, Hoffman and Streicher actually do it on by the height of expressions for reasons best known to themselves. Are you saying that you structurally recurse over some inductive type of expressions?
That's right. Yeah, we structurally recurse over the inductive type.
And you didn't say, but presumably your things are kind of de Bruynized, are they, the expressions?
Yes. Yeah. They are using the Brown indices. So this is this inductive type. There is a single one, and we structurally recurse on that. That's correct.
Did you find any difficulty in making your definition?
Um,
You know, there are very few fully formalized versions of what you're talking about in the literature or in existence, as it were.
yeah, my next slide mentions the formalization in Agda of the initiality project. I don't remember exactly what they did there, but if I remember correctly, it's almost the same as what we do. So I think there's not really much difference from the initiality.
Well, Agda would have real difficulties because it doesn't have an impredicative prop. So the way you treat partiality has got to be a lot worse than as it were just doing the normal mathematics, which you can do in lean.
Right,
I
that's a
think
good point.
there's also a initiality project formalization. There were two, right? There's one in Agda and there's one in Rock or Cock.
Mhm.
So I don't know if it's worth
Yeah,
continuing.
both of them are a nightmare. But uh, yeah, okay.
Yeah, well, maybe I
I mean, I think what I'm thinking is that when I've played around with this myself, it's truly very easy to write down a recursive definition that can't be seen to terminate. I mean, I think that's partly why they started to use the height of expressions rather than the structure of them. But um,
right. So our definition is actually structurally recursive and there's no termination issue. I mean, maybe one reason why that is so is that the syntax is like fully annotated. But
well,
I think
that's essential. I think I don't think you'd be able to do it without that. But I don't think that's the reason for why you're somehow succeeding more easily than one would expect. That's interesting. Anyway,
right.
love to
Okay.
see the
Yeah.
details sometime. But please, I'll shut up. Please continue.
Yeah, this might be a more in the weeds discussion that would be best left for later. Um, I think I just cannot answer this question well enough without actually looking at the details of what these other projects did. But as you mentioned, indeed, there was a previous formalization of this in Agda. I did not mention, well, so the four people involved here, I believe they work on both of the ones that were mentioned, so both the Agda and the Rock projects. I only mentioned the Agda one, but because I think the Rock one wasn't quite finished, but maybe don't take my word for it. Anyway, we have a similar theorem to what they had, which is that if you have a well-formed type in the syntax, then the interpretation of that thing is defined. And also, if you have two types that are definitionally equal, then they are just equal in the semantics, and similarly for terms. So this is what you would expect of this kind of construction. Yeah, the soundness proof is also not, it's just very long, but it's not particularly interesting. Great. Now I move on to the last part of this setup, which is this certificate producing proof assistant. As I mentioned, we have a attribute reflect that constructs a structure like this, including the deep embedding of syntax in this type expra that I showed, as well as some proof that this type is well typed according to the type theory. How does that work? Well, here's the pipeline. So we start with the so-called vernacular, which is what the user actually types in into the proof assistant. And then we pass the vernacular, let's say axiom P of type X, into the ordinary lean elaborator. And this is an important aspect of this that makes it somewhat easy to implement. It means that we don't need to write our own proof assistant. It's just lean handles of that stuff for us, including like running tactics and those things. As was hinted at before, you can't really use all features of Lean this way, but you can use some. So that's nice. The output of the elaborator, so this Lean machinery, is going to be some internal representation of the axiom at the end of the day. For instance, one like here, which includes a name for the axiom P, as well as its type, which in this case is just X. Then we have our own translation module. So the colored boxes are what we wrote, and the white boxes are Lean native. So this translation module translates expressions from Lean type theory to our type theory. This translation is almost the identity map, but importantly, it inserts all these typing annotations that are necessary for the interpretation function to be like definable, I guess, without too much trouble. And then that gets passed to the type checker, and the type checker produces a lean proof that this type, like this one here, is correct, or maybe some term has some type or whatever. I won't say too much about how the type checker works here, but it's based on normalization by evaluation, and it's basically a tactic. So it's like your goal is that type theory proves something, you type in, type check, and it does the type checking and produces you a lean proof. And at the end of the process, this proof is sent back to the lean kernel, which is important, at least because it means that we cannot introduce any unsoundness. So it's not like this is an extension, it's just all goes back into the original type theory. Right. So the final, well, okay, maybe I should pause for a second before moving on, in case there are questions. All right. The final part of this talk is some mention of like questions we have or issues and just general things that we would welcome contributions for. So the first one is, well, let's prove some things about the groupoid model. So I mentioned earlier that the groupoid model of type theory, it exists. It's maybe somewhat more interesting than the set model because these semantics of types now have more structure than just the structure of a set. And we would like to prove some things about it. So let me explain what we could consider proving. Well, here is a predicate on types that you can write down in type theory. So it says that A, some type, is a proposition, and the definition is that for all elements AB of A, there is a path from A to B. So sometimes path, people would write the identity type for that, because that is how you represent paths in type theory. I don't want to maybe introduce too much confusion with Lean's equality, which is different because it's prop valued. So I just wrote the path here. And here's an example of a groupoid that is a proposition. So remember, groupoid is a category. Every morphism is isomorphism. This groupoid has three objects, the orange things. And between any two objects, there must be an edge or an isomorphism. Furthermore, if you, well, all the diagrams commute. So like this path here, this isomorphism, has to be equal to this composition of the two isomorphisms. That is what a groupoid would be. That is a proposition as far as the type theory is concerned. But we can have some other ones. So the next step up in the hierarchy is sets. So sets don't necessarily need to have a path between any two objects. But if there is a path, it must be unique. So you can't have more than one isomorphism between these two orange dots here. And the way you describe that in the theory is like this. So you say that for any two elements of A, the path type itself between those two elements is a proposition. So it's kind of like recursive. Then the next step up is groupoids. So a groupoid is, here's an example of a groupoid that is not a set. And the reason for that is that it has two paths down here. So maybe topological interpretation is that this is some kind of hole in the space, whatever, but these are the kinds of things we can have in the semantics. And then you could keep stacking up this recursive definition. I mean, it keeps going on forever. But in the groupoid model specifically, there's no example of something that would be a true groupoid according to this definition, but not a groupoid. So that's like a particular feature of the groupoid model that the hierarchy just kind of ends at level groupoid. Okay, so that is something we would maybe wish to prove. This axiom that every type is a groupoid. As far as the theory is concerned, this is an axiom, but you can prove it in the semantics, and the point of this project is to connect the two. So this would be a nice thing to have proven, and this is something we are working towards. And then another fact about the groupoid model is that univalence holds for set level types. So you don't get the full univalence axiom as seen in homotopy type theory, but you do get this somewhat restricted one whenever A and B are sets. Yeah, so these would be nice things to prove. Next issue, type checking performance. Sorry, there's something in the chat. Okay, maybe I'll defer the question in the chat for later. Type checking performance. It's not great. And I think we have some reasons to, or like we have some suspicions for why that might be, but first I will explain these graphs. So the graph is as follows. The left graph, let's focus on that one. The x-axis is the time that Lean takes to type check a definition. The y-axis is the time that our type checker takes to type check the reflected definition. Okay, so this is the kernel time for Lean, and this is our type checker tactic. And the four colors of dots, those are four data sets of different kinds of terms. And you can see that for some of those data sets, our type checker scales linearly with Lean, maybe with a bad constant, but still linearly. However, for others, it goes up quadratically. So that's really not good because it means that you type something in and then it takes like a day to type check. The other graph is similar. It's again Lean on the x-axis, but on the y-axis now it's the size of the proof that we produce. It exhibits more or less similar behavior. Any questions about these graphs? All right.
Is the problem with the performance characteristics are fully understood, or is the problem just to optimize it?
So I think that's my next, just to repeat the question, it was whether we understand why the performance characteristics are like this, and maybe it's just a question of the optimization. So I think it is partly a question of the optimization. I mean, there are programming tricks that you could apply and various things you could do to speed it up. Maybe you could make it a reflective tactic, and that would probably help. But there's one kind of core issue that I believe Andy Pitts mentioned also in last week's talk by Steve, which is that, well, when you want to define the interpretation function the way we have done, you need to have annotations on all the pieces of syntax. So for instance, you cannot just have application nodes represented as a function f and an argument a. You need to have this additional piece of data here, which is the codomain b of the function. Right? And this is needed for the recursive definition of interpretation. However, let's consider what happens when you do that. So on the left-hand side is what Lean might do to type check in an application. And in Lean, those annotations don't exist, so you're just type checking FA. And by the way, I wrote it in bidirectional style. Lean isn't bidirectional, it's a lie, but it's true enough for what I'm trying to say. So how would you check that? Well, first you synthesize a type for F, and that should be a pi type. You grab the A, the domain type from that, and you check that A has that type. The argument should have that type. And there you go, that you've type checked FA. However, in our setup, that gets translated into the following typing derivation, where now, because we have this additional argument B, you also have to type check that, right? There's no reason why B has to be related to F a priori, like in the representation of the syntax. So you need to type check it. And there are some potential solutions to this that would be, I think, really interesting and good projects. I mean, one idea would be to prove a theorem, an elaboration sort of theorem that shows that you can coherently insert those, but you don't actually ever do that in the computational representation. And we also wish to thank Pesera Amarasakera, who showed up on GitHub one day and tried our system on some more interesting things. And yeah, it didn't scale very well. So they tried it on a proof of the structure identity principle, and it took 5 hours to type check. So this is an important issue that needs to be solved.
There are a couple of questions in the chat. So
okay, yeah, we can.
yeah. So one of them is maybe I'll save two of them for the end. But one of them is about when you look at the time that your type checker takes. Do you just look at the actual time of your metacode, or do you also include the time the kernel needs to verify the generated proof of well-typedness?
Yes. Good question. So in fact, we only look at the time the metacode takes. I measured everything. So I measured the time the kernel takes as well. And that time is negligible compared to the time taken by the metacode. Strangely enough, or I don't know if that's expected or not. But basically, the main bottleneck is the metacode. It's not the kernel in this case.
Thanks. There are two other questions, but I'll save them for the end.
Okay. Yeah. So let me just mention a few. extra things that would be they're not as crucial, I think, as like actually proving things about groupoids and improving the performance, but they're still interesting. So one issue is that our definition of the type theory does not include universe polymorphism. So you can't write, this is the reflexivity axiom for, or like constructor for paths. You can't write REFL parameterized over type U. You only have REFL 0 for type 0, REFL 1 for type 1, and so forth. So that's not really very usable. In Lean, you would just, like in ordinary Lean, you would write REFL parameterized by universe U. So the interesting thing is that because universe quantification in Lean is in prenex form, which means that the universes are all kind of upfront, but you can't, like for instance, you can't have a pi type over universes. That's not something that Lean supports. Agda does, but Lean doesn't. Because they are like this, we might not need any changes to the definition of the type theory, because probably you can take an axiom schema like this and make it a function from the natural numbers into a bunch of reflected axioms, right? So the fact that all the universes are upfront means that you can quantify them externally, which is quite convenient. Well, okay, this is a conjecture. I'm not sure that you can, but I think you can, and this would be a nice thing to implement. Okay, one last thing, mutual induction. We use it a lot for the syntactic meta theory and stuff. Support in in Lean for mutual induction is really not very good, unfortunately. So I end up writing a lot of kind of clunky theorems, and there's a lot of code duplication. There's early work by Jonathan Chan at UPenn implementing some better tactics for this, but I think this is an open kind of task that would be really beneficial for improving the state of like logic-y type proofs in Lean. And on the semantics side, some open questions, which I will not say much about, but my co-authors are working actively on this. Well, we have presented natural models briefly in this talk, but also there are other notions of model. You can have these things that we called elementary models. You can use PyClans. There are many ideas. And the question is, well, which of these, or one question is, which of these enables efficient model constructions? So what I mean by efficient is that ideally we have some very nice abstract high-powered theorems where you construct some basic but important data, and then the rest of the model kind of falls out of that, as opposed to having to, say explicitly, okay, here's the pi types, here's the sigmas, and so forth, like bit by bit, spelling out all the details of the model. Yeah, so we want efficient constructions of groupoids and maybe a simplicial set model eventually. And see these papers by my co-authors to learn more about that on path types and algebraic type theory and on polynomial functors and PyClans. Great. So last thing I will say is that all of this is part of the HoTTLean project, which tries to realize this idea of writing down both the synthetic side of things and the model-based side of things in a single system, in this case for homotopy type theory and its various models. So thank you for listening. And I guess we can move on to
Thanks a lot. Yeah. And we'll begin by taking a few questions. So there's one question by Andrew Pitts, following which we'll address the questions in the chat.
Sorry, it's me again. So I was very interested. Is it the translation step that you do is elaborating the syntax and putting in the decorations? Is that right?
Yes, it's putting in those annotations that are needed.
So I'm not aware of any results about when that is or isn't possible. So you presumably have something there that you could write about independently of this project. I mean, do we know theorems about when unelaborated syntax that's not decorated with any type information can be elaborated into the fully elaborated one? I mean, I wouldn't know how to do it, but maybe somebody does know how to do it, and it seems that you are one of those people.
So maybe one thing I should say is that this implementation that we have is not a theorem, right? It's a tactic. It's just like a piece of code.
I think you should go away and prove a theorem.
Yeah, I agree. And the reason for that is what I said, which is that if you have a theorem in principle, you can then actually not run the code. And this would be important for performance reasons. but I don't know much about this, to be perfectly honest. So I can't answer that question in any capacity besides like, yeah, I agree, it would be nice.
Thanks. So there are a couple of questions in the chat that popped up over the course of talk. So there's one by SC Steenkamp, who says that Awodey touched on this last week, but why do we do this in Lean rather than writing a new proof assistant? And aside from the feature, aside from MATLAB, or is that the main reason? Are there any features of Lean that are particularly beneficial to this project that would be hard to implement from scratch?
Right. Yeah, this is a good question. I think there are two main, well, it probably also depends who you ask, but if you ask me, there are two main reasons. One is MATLAB, so you cannot push MATLAB aside. And the reason is that we want to build the groupoid model. We want to build simplicial set models. Actually, I believe that the model category structure, like one of the Quill model category structures that are important for this have recently been formalized, if not in MATLAB, then at least downstream from MATLAB. So there is a ton of results that already exist and have been formalized that we can reuse, and this is important. That's one reason. The other reason is that Lean, it's the proof assistant has very extensible syntax. And so we can implement various macros and elaborators and this pipeline that I showed where we send the code first to Lean and then it goes back to us and then we translate it and so on. This is easy to do in Lean in general. And well, I cannot comment too much on how it would be in other systems, but I think it would be somewhat more difficult to do these kinds of things. Yeah, so hopefully that answers it.
Thanks. There's another question that piggybacks on the first one. So, which says that, so Derek Sorensen says that, I seem to recall that John Sterling is working on a new proof assistant and cares about HoTTLean questions. I wonder if that would be a candidate. The question is, why do you need SynthLean? Why does Lean itself not suffice to reason about the type 3 model of HoT?
Right, so I guess there are two questions here. Well, maybe I'm not entirely sure what you mean by candidate here. I guess maybe the question is whether we can like use pterodactyl, I believe is the name of.
Oh, yeah, sorry. I'm not up to date on what John like. I'm not up to date on these kinds of things, and I was just thinking, based on the first question, if there's if there were to be a proof assistant that were like built for HoT and were the best possible proof system, I've wondered if I wondered what John Sterling's work, the progress was. And then unrelated to that, I guess I just don't understand why you can't use Lean itself. What is the purpose of SynthLean, and why can't you just use Lean itself to reason about your model of HoT?
Right. So SynthLean isn't really like a different proof assistant. Maybe I should change the wording on that front. It's an extension or like a library for Lean or a package or something. I mean, we are basically using Lean to reason about models of type theory. Like all this stuff on the semantic side is just ordinary Lean theorems. There's nothing special about that. The reason why we need some of this elaboration machinery is that on the side of the syntax, you really, really do not want to write like formal typing derivations by hand. And that's the point of a proof assistant, is to generate these types.
Right. Oh, okay. Yeah. So is Lean like the meta, kind of like a meta language over SynthLean?
I'm not sure if that's, I would word
Oh,
it.
never, oh, okay.
I would say SynthLean is like a package implemented in Lean. That's really all it is. It's a package that can take,
Okay, that makes sense.
and it can take Lean definitions and produce you some typing derivations from those automatically, which is convenient and nice, and that's why we have it.
Okay, that makes sense. Thanks.
Yeah, and oh, as for John's work, I mean, I don't know what the project is on, what the progress has been on pterodactyl. I will say, as far as I understand, John's goals are more to innovate on the just like purely how do you make a really good proof assistant for HoT, whereas our goals are more to do with models. Like we really want to have to relate this syntax with its semantics. So it's just somewhat different objectives. Okay, it looks like there's one more question in the chat. I can just read it out by Ohad. Hi. So question is, in a much simpler settings, we were able to use models and reflection to extract / pretty print a certificate for the reflected program. Have you experimented with models like that? Maybe I don't quite understand the question.
I can try to explain. I mean, so
Okay.
your elaborator, right, builds up all the missing information, right? That then needs to be kind of checked against the model's notion of paths, right? If those paths record the proofs that your various conversions have to be equal, right? What you get in your internal model when you externalize is the proof that your original program, right, was well typed. So you can kind of get your tactic to certify the program and pretty print that. I can send you some references, but we did it in a much simpler setting, right? It was just algebraic theories. It wasn't, you know, this kind of level of sophistication. But it's kind of would be cool if you could do that.
Sorry, I feel like I still don't quite get what.
I can take it offline if you don't want to take it.
Talk about it more later. All right, one more question from Andy Pitts. So, right, is there a switch that allows one to turn off the features of lean that do not belong to lean minus, whatever lean minus is? There is not. Our elaborate, like the reflect macro does try sometimes to detect if you've used something wrong early on and give you a nice error for that. Like if you type in, you know, there's some proof, you type in choice in one of the like subterms, ideally you would get an error exactly on that choice term, just in terms of the user interface. But yeah, there isn't really kind of a global switch. I mean, there are some cultural reasons for this. See you, Steve.
So kind of a related question to that. So let's say you construct a proof that uses classical logic, and then you try to reflect it. I imagine what you end up getting as a result is that in the theory that contains classical the choice, you have kind of like a proof that corresponds to the one that you're trying to reflect. As in, it doesn't necessarily like as in like it doesn't as in like there is the option of also accommodating classical proofs, but also the option of kind of enforcing constructiveness when needed.
Yeah, that's correct. So I should be clear about that. The features that we don't support really are like built-ins of type theory, like proof irrelevant prop. But we do support axioms. So if you do use choice, that we can reflect that. It's just that probably you might have trouble finding models, but you can certainly reflect it.